So today we're going to talk about the mathematics of board games. Now, play is part of being human, and archaeological evidence of games dates back many millennia across all civilizations. Some games, though, endure, and they continue to hold our interest no matter how many times we play them. And I'm going to make the case that there are good mathematical reasons why this is so. Part of our exploration can be encapsulated in the question, why are there Grandmasters of chess, but not Grandmasters of noughts and crosses? And the answer to that leads us to develop the ideas of mathematical complexity, which is kind of a way to measure how big a game is in some sense. And along the way, we're going to meet the machine that played chess with both Benjamin Franklin and Napoleon Bonaparte, and we're going to find out what is the hardest board game of all time. So I've said board games have been played for thousands of years. We have some evidence for this archaeologically. So we find these beautiful gaming boards. This one originates from the ancient Mesopotamian city of Ur, and it's called the Royal Game of Ur. It's a game that perhaps we don't play so much nowadays. However, it's got several things and characteristics in common with some of our modern games. So it's a game, it's a race. You have to get your 7 counters from safe initial point all the way along down the central row and then round to home, and then they're safe. But meanwhile, your opponent is doing the same thing with their counters on their side of the board, and you both are having to traverse this risky middle row where if your opponent lands on one of your counters, then that counter gets sent home. So we've all played games that are similar to this. You don't have free choice entirely. So there is some chance involved as well as skill, because you have these 4 kind of tetrahedral dice that you roll, and that determines how many steps you can move, how many squares you can move. So it's a mixture of chance and skill, like many games. Very entertaining. The rules for this were lost for a long time, thousands of years, but were rediscovered by a brilliant researcher at the British Museum, Irving Finkel. And you can look up, he plays a game of this on YouTube, and it's very, very entertaining. He found out what the rules were, and now we can play this game again. It's a brilliant game, but do not think that, this beautiful gaming board that we see here means that these games were the preserve of the wealthy only. Anyone can make, and this is an example of a board that was just scratched onto the base of a large statue, so you can just scratch your board and play a game of get a few pebbles. You don't need very much. So everyone's playing these games, and that continues to today. We don't need to buy an expensive set. We can scratch out a Parcheesi board and play a game, again, find a few pebbles, play a game. So we don't need equipment. These games can be played by anyone, anywhere. So that's brilliant that they're so universal. Another thing we should notice is that games are not just played for entertainment. There are different reasons that we have for playing these games. Of course, we want to be entertained, but also there's often a religious, spiritual, or moral aspect to the game. So on the left, here you see, this is the tomb of Queen Nefertari, the Egyptian queen, and she is playing a game of Senet there, an ancient Egyptian game. And the movement of the pieces in that game is an analogue for your journey to the underworld. On the right, you see a game that looks a bit like our modern Snakes and Ladders, but it originated, that game, from a much older game that came from India, and it's got this moral dimension to it that the ladders correspond to doing good deeds that get you closer to enlightenment, and the snakes are when you do bad deeds and they get you further away. So there's this other dimension to a lot of games. A final important dimension is a sort of analogy with a war, a conflict. You're fighting against your opponent and you're learning strategic thinking. So this is a game of 9 men's Morris. That goes back at least 2,000 years. Roman soldiers played it in ancient Britain. Now this game, just to give you an example board there, you each have 9 pieces and you place them on the board. Every time you make a row of 3, you're allowed to remove one of your opponent's counters. So it's a game full of strategy, a really fun game to play. If you've never played it, I recommend it strongly. And of course, chess, I guess, the ultimate thing we think of if we're thinking of a game that has got even the pieces, kings and queens, are fighting each other to the death. Well, when we are playing all of these different games, Each game has its own particular flavour, and the experience of playing the game will depend on various factors. And as part of our kind of exploration of the mathematics of games, I'm going to just mention 3 factors that really influence our experience of each game. The first one is, how complicated are the rules? And there's a continuum we can think of. Low complication, something like noughts and crosses, otherwise known as tic-tac-toe, or X's and O's in some places. That is a game I can explain. I'm sure you all know the rules, but we can explain the rules of that very, very quickly. We've got a square board, 3 by 3. Each player plays their counters in turn, crosses and noughts. You take turns until somebody gets a row of 3, and then that person's the winner. If it doesn't happen at all, then it's a draw. Right? Done. We now fully know the rules. Very simple. Here's another very simple game. It's called Domineering. This is a good game because you can play it probably with gaming pieces you already have at home. Take a chessboard, for example. You can actually play it on any size grid. And then the first player places a domino horizontally and will continue to place them horizontally. The second player plays vertically. They place their dominoes vertically, and you keep going, placing them wherever they'll fit. Each one covers 2 squares until somebody can't move. And the last person to place a domino wins. So at some point, the board is filled, there isn't enough space, and the last person who's actually managed to put a domino down will win. This isn't the complete game. So again, super simple rules. Very easy to learn the rules very, very quickly. So those games are at the low end of the complexity spectrum. Then a bit higher, the medium kind of games will be chess, backgammon, those kind of games where obviously we couldn't explain the rules in a minute, but if we spent an afternoon playing those games, then you'd know what the rules are, and you wouldn't have mastered them, of course, but you would at least know what the rules are. Now, there are higher levels of complication in games, and I had a look around. What might be the most complicated game with the most complicated set of rules? I think it's this. This game, the campaign for North Africa, almost isn't a game. I mean, what is a game? It's more of like a very, very long history lesson. So it's recreating this part of the action in the Second World War with the opposing forces in North Africa. The board is divided into hexagonal cells. Each turn you have to do a whole long series of things. You've got to, I think you always have to invade Malta for some reason, but poor Malta. But you have to make sure your troops have fuel and food and water, and the detail. Here are some of the instruction books and the things you need. The detail is extremely, extremely precise. For example, the troops have to have enough fuel. So everyone except the British troops, their fuel stores evaporate at a rate of, I think it's 3% per turn. The British fuel evaporates at a rate of 7% per turn. The reason for that is that in the actual Second World War, everyone except the British stored their fuel in 50-gallon barrels or tanks, and the British stored theirs in small jerry cans, so theirs evaporated faster. This is the level of precision of this game. Here is the board. It's over 3 meters long. It's been estimated a single game would take 1,500 hours to play, like your first game of this. Just, kind of a practice game. If you give up everything else, give up school, give up work, and full-time spend 35 hours a week playing this, it's going to take you 43 weeks. And then, if you do win, your opponent immediately wants a rematch, right? So it's a full-time job. This is on the high end of the complexity level. There it is. We are going to concentrate much more on the games over to the left-hand side. So that's complexity of rules, how complicated the rules are. The second aspect, how many players? The game, obviously, that's a very important part of the game. Now, there's kind of no upper limit, theoretically, but we are sitting around a board, so there's a practical limit. Most games have, a single-figure number of players that are ideal. I did find one that had 7 players, designed for 7 players. This is called astronomical chess. I don't know why, it's got nothing to do with chess, but you can see the board is heptagonal. 7 people can play. A game like Monopoly, classic Monopoly, has 6 tokens, so up to 6 people can play. But most board games are based on square boards, and that lends itself to 4 players, a maximum of 4 players, like Ludo here. You're set up 1 person at each corner, so at most 4 players is quite common. 3 people can play this game, but a good game perhaps for 3 players is Chinese checkers. It's nothing to do with checkers. It's also not Chinese, having been invented in Germany in 1892. But never mind. Good for the marketing, right? So this game, because the board is a hexagonal or a six-pointed star, it's quite good for 3 players because if there's 3 of you, then everyone has an opposite pair of triangular sets of counters. So that's okay for 3 people. But the games we're going to focus on today, the board games today, are going to be 2-player games, like all the classics, drafts, checkers, mancala, all its variants, backgammon, chess, those, and noughts and crosses, and many others. Now, of course, you need 2 people at least to play a game, don't you? Well, no. Solitaire is a game you can play for 1 player. So this is a game where you have to take marbles by jumping over them, and the ultimate aim is to end up with just 1 marble left. It's quite challenging and difficult, but very good fun. Okay, game for 1 player. You can't have a game for 0 players, though, can you? Well, I give you John Conway, great mathematician, and he invented the game of life. So this is an example of what's called a cellular automaton, actually. It's a game that plays itself, a game for 0 players. All you do is you pick an initial configuration. So that's the only input. And so the configuration is you have as large as you like square grid, and then you select some of the cells, some of the squares are going to be alive to begin with. I've coloured them green there, greenish. And then at every step, there's a precise collection of rules, there's a precise algorithm for what happens next. And so cells come alive or die according to various rules. And the rules say, it's sort of somehow mimicking a population growth. And it says, okay, if a cell doesn't have enough neighbours, it's going to die because it's too isolated. And if a live cell has too many neighbours, it will die because of overpopulation. So what are the neighbours of a cell? Well, every cell, this one here, every cell has 8 neighbours, the immediately surrounding 8 squares. So if there's a live cell and it has fewer than 2 neighbours, it dies, or more than 3 neighbours, it dies. And if the other cells that aren't live, they're dead cells, any dead cell that has exactly 3 live neighbours will become alive next time round, and everything else stays the same. So we can see what happens with this initial configuration. The live cells at the corners of the rectangle, they each have exactly 3 neighbours, so no change, they stay alive. But the ones in the middle of the rectangle, they have 5 neighbours, 5 live neighbours, and so their overpopulation, well, they will die. And a couple of cells, the cells immediately above and below the middle ones, they have 3 live neighbours, so they become alive. So that's the rules. This configuration now is actually quite an interesting one because this stays the same. At this point, no dead cell has exactly 3 live neighbours, and all the live cells have 2 live neighbours, so everything stays the same. So it's just fixed at that point. But there are so many amazing and interesting things that can happen in this game. This is a real object of study and interest to mathematicians. This kind of thing can happen. So in this situation, it sort of cycles periodically through the same 3 designs forever and ever and ever. You can make spaceships. This one's called a glider, and it carries on forever and ever and ever, moving diagonally down the board to infinity. You can make machines. This is a machine, it's called Gosper's gun. It fires gliders at regular intervals, forever. This is fantastic. You can do so much with this game, depending on the initial configuration. You can create machines that are self-replicating. You can create logic gates, and if you can make logic gates, you can make computers. And if you can make computers, maybe you can make a computer that plays the game of life. So there's so much fun to be had with this game for 0 players. So those are the extremes, how many players you can get. The third really crucial characteristic of any game is what proportion is chance and what proportion is skill. Here is the kind of spectrum here. At the bottom, 100% chance. You don't get to make any decisions, you just follow what the roll of the dice will tell you to do. Snakes and ladders is in that category. You don't get to make any decisions at all. In the middle there, we've got games like backgammon where there is lots of skill involved, but there's also some chance and luck because you are rolling dice to determine how many steps you can take. At the top, and this already tells us we're going to need something more than this chance versus skill spectrum, because games that are 100% skill include noughts and crosses, which obviously it's not a very hard game, but you are making all the decisions there. There's no luck involved. Connect Four is another one, chess. So those kind of games. And these are the ones we want to consider and talk about more the rest of our time. So from now on, the board games we're going to talk about are going to be games for 2 players that do not involve chance, so it's pure skill, maybe not very much skill, but pure skill. And the final technical requirement I'll mention is that they should be games that have perfect information. What that means is the players both have access to all the information about the game. No one's got any secret hidden things. We're not playing Cluedo or anything where everyone's got a sort of different piece of the puzzle that they can see. Everyone knows exactly what's happening in the game all times. So those kind of games are what we're going to think about. And we can already see, as I've said, just knowing that a game is 100% skill, 0% chance, does not really tell us how hard that game is. We know noughts and crosses is easier than chess. So how are we going to sort of tease out those differences? Here's where we start to think about complexity. So the first measure of complexity in this context is what's called the state space complexity. And the question really is we're asking there is, how many different positions can the game be in during the course of play? Because if there's only 3 different configurations we can be in, we could learn each one and we could learn what to do, and that would mean, presumably, it's quite an easy game. But if there's 100 billion squillion, that's a big number, of positions, maybe then it's harder to develop a strategy. So this is one measure. It's called the state space complexity. So we can do a couple of small examples. Noughts and crosses, how could we count the number of possible ways that the board could look? Well, we can say, okay, there's 9 squares, and at any one point, each square is either empty, it's got a cross in it, or it's got a nought in it. So there are 3 possibilities for each square. And there are 9 squares, so it's 3 for the first square, times 3 for the second, times 3, times 3, times 3, and so on. That gives you 3 to the 9 possible configurations, which is sort of 19 and a bit thousand. But that's clearly an overestimate. Why is it clearly an overestimate? Because it includes things like this that can never arise. That can never happen in a game of noughts and crosses because we alternate. So pick one to go first, but let's say crosses go first. Then we go cross, put a cross down, and then a nought, and then a cross, and then a nought. So you never get all crosses on the board. So we can count in a slightly different way. We can say, okay, we could have a completely empty board with no pieces. That's one possibility. Or what about if it just has one piece? So where can the cross go? There's 9 places it could go. So there's 9 boards that have one piece. What about having 2 pieces? Well, there's 9 places to put the cross, times 8 places, there's 1 fewer available to put the nought, so 9 times 8, 72. And you can carry on like this. The calculations get a bit more complicated, but you can carry on like this. It's not too bad, and you come out at about 6,000 possibilities. So the state space complexity we could estimate as 6,000. That's what you can do without having to think too hard. But it has to be said, there are still some duplicates and repetitions here. Oh, sorry, not repetitions, some illegal spaces here. Because this, for example, can never arise. We never get both players having 3 in a row. Because when you get 3 in a row, you've won, the game finishes. So this game would have finished when we got 3 crosses. So this can never arise, that configuration. So if we eliminate those illegal configurations and just stick with the legal ones, which you can sort of do by brute force, it's about 5,500. There's one more efficiency saving that we can make, and that is to do with symmetry. This configuration really is the same as this one, because all you've done is rotated the board. It doesn't actually affect anything about the game to do that. So there are various, you can reflect, you can rotate, and end up with basically the same game, with not any difference made to any strategy you might develop. If you do that, then you actually reach a smaller number, 765. And that is the state space complexity of noughts and crosses. Feels like a lot, right, for such a simple game, but as we'll see, this is nothing. This is nothing. Let's look at a slightly more complicated game, not noughts and crosses, Connect Four. So this is played on a vertical board, and the aim here is not to make a row of 3, but to make a row of 4, vertically, horizontally, or diagonally, somewhere in that board. There are 7 columns Each one has space for 6 counters. So one player is red counters, one is yellow. You alternate putting them in. Of course, they will drop down to the bottom of as far down as they can go in the given column that you put them into, and then the first person to make a row of 4 will win. So, in this case, we can't do that thing we did for noughts and crosses of saying every space is either empty, red, or yellow, because if you've got an empty space at the bottom, then you can't have any full spaces above it, because they just fall down. So we have to think slightly differently here. Let's imagine a single column. This, by the way, is my favorite slide of the entire talk. Very, very exciting. I'm so happy that I managed to do this. So for each column, it could be empty, right? That's one possibility. Let's say we have one counter. So proud. So it could be red, right? Or it could be yellow. There's 2 possibilities then. What about if we have 2 counters? So there's 2 possibilities for the bottom one, and then the next one can either be red or it can be yellow. So 2 times 2 is 4 possibilities for having 2 counters. And if there were 3 counters, it's times 2 again, and 4 and 5 and 6, so on. So you can add up all of these, you get 127. So this is how many different ways you can partially or fully fill this column. But we've overcounted again. There are some illegal positions in here. You could have 4 yellow counters, that would win you the game, but you'd never see a 5th counter going in because the game is over. So there are some illegal configurations in there. If you take away those, you get 111 legal columns. So you could say, all right, well, there are 7 columns, each one 111 possibilities, so we'll do 111 raised to the power 7. That's the state space complexity. That's about 200 trillion. You could do that, but that would be, again, an overestimate. Why? Because obviously the columns are not just in isolation. You have 7 of them next to each other, and if you at any point get a horizontal line of 4 of the same color or a diagonal line, then the game finishes. So this is an overestimate. It's not too bad, but it still is too many. It can be calculated by brute force, not by me. A computer calculated that actually there's about 4.5 trillion possible, genuine, valid legal positions that the game can be in Connect 4. That's the state space complexity. Now, normally, we can't give an exact answer. Anything much more complicated. I mean, this is already far too hard for a human to do. But, you get tired and fall over. You can't calculate an exact answer usually. So normally we just say what it is to the nearest power of 10, best estimate. So for this, it would be 10 to the power 13. For noughts and crosses, 10 cubed is the nearest power of 10. Well, that's one thing we can calculate, the number of different configurations. But actually, maybe what we're interested in is how many different games you can play, how many different ways there are through the game to the end. Because any of these configurations might turn up in lots of different games. Really, if we're thinking about how we can make a strategy, we might be interested in what are the different outcomes of the game and how we get there. So the different games that can be played. And to explore that, we need something called the game tree. So the game tree, by the way, I have to warn you, mathematical trees are always upside down. Trees have branches, right? And so this is a tree because we're going to, at each point, our decision about what to do next, the possible moves, are going to be branches that come out of that point, and then we'll get smaller and smaller and smaller branches. So here's my tree. This is the beginning of a game of noughts and crosses. So, starts off with an empty board. Crosses go first. There are basically 3 choices. The cross can go in the center, it can go at a corner, or it can go in the middle of an edge. That's your options. So 3 branches. And then, let's take the left-hand branch. What can noughts do? Where can we put our nought? Well, there's 2 options this time, really. Once you take account of moving the board, rotating the board, you can either put your nought in the middle of an edge, or you can put it at a corner. 2 options. And there are more options in the other cases, which I'm not going to draw, and more options, and you can keep going and keep going. This already is too big to fit on a slide. So this, even noughts and crosses, the game tree is sort of big for a human being to actually conceive of. I wanted to give you a full game tree. It won't be for noughts and crosses. So I picked domineering. Remember we talked about domineering, but like on a chessboard, you can play it on a smaller board. Same rules. Player 1 places their dominoes horizontally, player 2 places them vertically. So if you are playing a game of 3x3 domineering, there are just 2 choices really for where you can put your first domino. you can rotate the board, and reflect it, but basically either you can put your domino along an edge, or you can put it so that it covers the center square. Those are your options. Now, let's focus in on the left-hand side, the left-hand fork of this. What can red do? Player 2, they've got to put their domino vertically, and there are 4, you can easily see there are 4 places they could put it. In one of these places, this one, that's a winning move, because where can blue put a horizontal domino? Nowhere. There's no space for a horizontal domino after at this point. So red has won the game at that point. But the other 3 are not yet a victory for anybody, so you carry on. Here is that whole left branch. Here is the whole game tree. We're not going to look in detail at it, but I wanted to at least, I feel I've managed to fit one on a slide. That's the smallest possible game I could think of that made any kind of sense to do. Here is the whole tree. Now, at these endpoints where the game finishes, these are called the leaves of the tree. For obvious reasons, that's the last thing you get on a tree. And here they are, I've highlighted them all. The game tree size, that is the word we use for the number of leaves on the game tree. And that is because each one of those represents an individual, a specific game. So you can follow back from a leaf, you can follow all the way back to the beginning, you can see all the moves that have been made, it specifies a unique game. And these are all the possible games. There are 11, 8 of them are won by blue, 3 of them are won by red. So that's the game tree in this very, very tiny example. 11 games are possible. There's a related concept which I intend immediately to conflate with game tree size, and it's game tree complexity. It's slightly different because this is the number of leaves on the smallest part of the game tree that allows to fully determine the outcome if everyone's playing optimally. So not just sort of moving at random, maybe you choose the best move in each case. As we saw, if red chooses that particular move, they can win straight away on their first move. So we don't really worry about the other little bits of the tree. However, often, in fact, almost always, we are having to estimate this. We don't know this, so we say we'll estimate it by estimating the game tree size, the total number of leaves. That itself is also an estimate, almost always. And so I'm basically, as I said, I'm going to essentially treat these as if they're the same thing, because almost always our estimates are estimates for both of those. Okay, so here's a few little examples. Game tree complexity. So 3x3 domineering, 10 to the power 1. As I said, we always pick the nearest power of 10. Noughts and crosses, 10 to the 5. And the exact number is there. I've said assuming arbitrary stupidity. You don't even notice that your opponent has 2 crosses already, and you should fill in the gap there. I'm taking account all possible moves. You're most absent-minded and not paying attention. This is the size of the game tree. Connect 4, bigger, 10 to the 21. Possible games of Connect 4. 8x8 domineering, the full-size one, bigger than that even, 10 to the 27. So it grows very quickly. We can see why at some point we approximate. We do not want to count actually the exact number of games of 8x8 domineering or whatever it is. So this is all interesting stuff. But of course, when we play a game, we usually want to win. Can this help us win? Can we use all this stuff for the game tree complexity to find a winning strategy? Well, if you happen to actually have the whole game tree, then yes, of course you can. Say you're blue, you're the first player in 3x3 domineering. Look at the right-hand branch of that tree. You can see every outcome there is a win for blue. So to win this game, all blue needs to do is make sure they're in the right-hand fork. In other words, their move should be cover the central square, and that will win for them. So we can find a strategy if we have the whole game tree by just sort of looking at what the best option is at any moment. Normally we don't have the whole game tree because they get very, very big. But this game, we could say absolutely, this is a solved problem. So we say a game is solved if we know how to get the best outcome possible. We might not always be able to win. Maybe we can force a draw at least. But that's what we mean by saying it's solved. However, there are little qualifiers to the word solved. There are 3 kinds of being solved. You can be strongly solved, like 3x3 domineering. That means you can be parachuted into the game at any point, whatever's happened so far, and there'll be an algorithm that tells you how to make the best of it. You might not always be able to win, but how to make the best outcome, starting from any point. Weakly solved is there's an algorithm known from the start of the game. that will give you the best outcome you can achieve. And then there's this weird category, ultra-weakly solved, which says there is an algorithm which will allow the best outcome from the beginning of the game, but we don't know what it is. How can that be? Well, we'll come back to that. So examples of strongly solved games, 3x3 Domineering and Connect 4, both strongly solved. 3x3 Domineering, we already know the strategy. It's try and cover the central square. And actually works for red as well. If blue fails to cover the central square, if red then does cover the central square, red will win. So that's a full strategy that works throughout the game. Connect 4, I am not going to tell you the full strategy, because although the first player can guarantee a win, it will take up to 41 moves for them to do that. So I'm not going to talk you through those 41 moves, but I will just mention that it's crucial what you do first. So that little kind of schematic there tells you if the first player plays the middle column, then they can force a win. If they go in either column immediately adjacent, they can only guarantee a draw. And if they go in any of the 4 outer columns, the second player can guarantee to win if they're playing optimally. So those are strongly solved. Some weakly solved games we know about, drafts, aka checkers, Nine Men's Morris. Those are both weakly solved as a strategy from the start of the game. What about this ultra-weakly solved thing, which is so weird? Well, I'm going to present to you, this is going to be a brilliant game. If you've never played this, it's the only game I know of that involves eating the board as you go along. Be careful what your board is made of. So this game is called Chomp. You have a rectangular board of some dimensions you can determine in advance. And the idea is when it's your turn, you eat a square, and then you have to eat all the squares below it and to the right. So you keep going, doing that as an example game here. And we all know it's really rude when you're sharing a bar of chocolate to be the one who eats the last cube, yes? That's really rude. So as a penalty for this, terribly rude behavior, the person who eats the last square loses the game. Okay, so this game you either win or you lose. I claim that there is a strategy that will allow player 1 always to win. There's no draw in this game because someone will end up eating this square. But I don't know what the strategy is. This may not be very helpful. But we can prove that there is one. And what you do is this. Let's say that's not true. Let's say that player 1 doesn't have a strategy like this. So that means player 2 could force a win. If player 2 could force a win, then they've got a strategy that whatever player 1 does, they've got something that they can counter that and ultimately win. Okay, so what player 1 will do is this. Say, okay, if my first move is to eat the bottom right-hand square, then player 2, we know, by our assumption, which is going to turn out to be wrong, by this assumption, is going to have a counter to that, some counter move X, we don't know what it is. Now, what player 1 is now going to do is to steal that strategy. Player 1 steals that strategy, and instead, they don't open with bottom right-hand square, they begin with move X, and obviously have the rest of the strategy in mind. So you might think, okay, it looks like they're in the same position now that player 2 would have been in and player 2 can win, but maybe it's not because the bottom right-hand square is already missing, so maybe it's not identical. However, in this game, remember, whatever square you eat, you always eat all the ones below and to the right. So any move you make will involve eating the bottom right-hand square if it hasn't already been eaten. So after this move X, whatever it is, the bottom right-hand square will not be there, so this is indistinguishable from first eating the bottom right-hand square, then doing whatever move X is. So this really is, you can steal their strategy without any worries, apart from the moral worries. So player 1 can always win. So this proves that this game is ultra-weakly solved. Player 1 can always win, it's just we don't know how. So I suggest we all go home and practice extensively this game until we know what the strategy is. Okay, so there are levels of being solved. But let's talk about chess. Chess is not even ultra-weakly solved. However, we all also know that computers are very good at chess and can beat even the best players. So how is that happening? Well, it's interesting that, in fact, machines that play chess are older than we might think. In 1770, a chess-playing automaton called the Mechanical Turk wowed the world. This automaton, so that's not a human there, that's this automaton that, that moves and plays chess against you. It toured Europe and America for 80 years, and it played chess against and beat both Napoleon Bonaparte and Benjamin Franklin. And Edgar Allan Poe wrote an essay about this, and he thought it was a hoax. He said, and here's his reasoning, and I find it very interesting that this is the reasoning. He said, it can't be a machine, because machines have a thing that they follow, a process that they follow. They don't make mistakes. They're not like, there's no human error with a machine. So the fact that this machine sometimes loses, it's very good, but it doesn't always win. Therefore, it must be a hoax. There must be a human who's secretly playing. That's a very interesting take. It's wrong. It's a wrong take, but sadly, the conclusion, even though the argument was wrong, the conclusion was correct. Here is the inside of this machine. You can see there's lots of gears and levers and stuff going on, but there's suspicious, large empty space on the right-hand side, and even more suspicious, a rug and a little cushion. Almost as if to make someone more comfortable. And indeed, unfortunately, it was a hoax. So inside this machine, there was a very, very good chess player. We even know the names of some of the good chess players who were actually playing, being the Mechanical Turk over the years. They were playing against a human, a very good human, but yeah, it was not really a chess-playing machine. So when's the first chess-playing machine? You can be thinking, what do you think it is? Well, would 1912 surprise you? Okay, slight demurral of this. It was a machine that could play a specific, special kind of sub-game of chess. It knew how to play a particular endgame and to win at that endgame. The endgame in question is where the machine has a king and a rook, and the human player just has a king. So obviously, the machine, slight advantage. But it was still pretty amazing for that time that this could be done, that a machine could be built that would do this without any human involvement. And the reason it could do it is because that very specific sub-game is strongly solved. There's an algorithm that can be followed by a machine kind of mechanically, and it would win every time. That's pretty amazing. It wowed the world when it was put on show in Paris in 1914. But what about real chess computers? When does these start to come in? Well, there's a groundbreaking paper in 1950 by the mathematician Claude Shannon, there he is, who wrote a paper called Programming a Computer for Playing Chess. And he wasn't saying, here's my program. He was saying, what are the challenges of this, and then how might we address them? And in that, it was kind of a really early paper in this sort of area, and he talked about the complexity of chess. So he was thinking, how many possible games of chess are there? What we now call the game tree complexity. So here's how he did the calculation. It's very difficult to do this, but here's a good estimate. So the first thing you need is what's called the branching number. When you're playing a typical game, think of the game tree, how many branches are coming out of each node, on average? So it's not always exactly 30, but the average number is 30. It might be less at the end of the game when you've only got your king left or whatever, but on average, during gameplay, it's 30. How long does the game last? What's a move in chess? This is sort of a technicality, but a move, actually, strictly speaking, in chess, not in all games, but in chess, it's white does something, then black does something. So actually, that's what we might actually think of as two moves. To make this distinction in the area of game complexity theory, or combinatorial game theory, which is what we're talking about now, that's the name for the mathematical subject we're talking about. To make this distinction, we say a turn for an individual player is called a ply, and the plural is plies. So a move here is a ply for white and then a ply for red. For black. So if there's 30 choices for each ply, then a white then black move would be roughly 30 squared, which to the nearest power of 10 is 1,000, 10 cubed. Okay, so we know how much choice you have for each move. How many moves are there in a game? Well, data from lots and lots of games says that in a game between good players, there are about 40 moves, 40 kind of exchanges of turns. Now, a game between good players is important. Bad players tend to fight to the death when they should resign. I should know, I'm a bad player. So their game's gone a lot longer. But yeah, about 40 moves. So you can then use that to estimate the game tree complexity, because you say, okay, at each of these 40 moves, there are 1,000 options, so it's sort of 10 to the 3 times 40, 10 to the 120. That's now known as the Shannon number. It was a kind of an early estimate for the game complexity of chess. Now, even modern computers have an upper limit of around a quintillion calculations a second, 10 to the 18. There's no way that can happen. They are not going to be able to find the whole game tree. So we've got to think of something else. Well, what about, says Shannon, what about instead we imagine a database? A computer could have a database of all the possible legal positions. So now he's talking about the state space complexity, right? How many legal positions might there be? And then, so a lot. Let's see if we can have an estimate for it, he says. And then you could imagine in your database you have each legal position and then the best move when you're in that position. So can we estimate that? How many legal positions there are? What's the state space complexity? Well, here's a chessboard. It's got 64 squares. There are some pieces. Each side, each player has 16 pieces, at least to begin with, so 32 pieces, and they've got to go on the board. Let's forget that sometimes, there are fewer pieces than that. Let's just pretend we're looking at when there are 32 pieces on the board, where are they going to go? If you want to worry about sometimes there aren't on the board, perhaps you say there are 65 squares on the board, and some of the pieces may be in square 65, i.e. they've been taken. But just for the moment, let's have 64 squares like we would expect, and we've got to put 32 pieces. So let's say the white king, he's got 64 places it could go, so 64 choices for that. Then where's the white queen going to go? There are 63 remaining squares the white queen can go in, and so on and so on and so on. And so you get something like this, all the way down to 33 places for the very last of the 32 pieces you're going to put down, leaving 32 blank squares at the end. So is that a good estimate? No, it's really not. I mean, there are many reasons why it's not, but there are one important one that Shannon takes account of in his calculation in his paper is that this duplicates an awful lot. Here's why. There are several pieces that there's more than one of. So, for example, white has 2 rooks. And when you put all the pieces down, you can't distinguish which one of those rooks was placed down first. So that means you're going to get that precise configuration twice. The first one goes down on the green square, or the first one goes down on the white square. So you've doubled the amount of positions that you're trying to count. So you've got to divide by 2 because of that. And there are lots of pairs of pieces, knights, bishops, so on. There are 6 pairs of pieces for which you have to worry about this. And even worse, or better, depending on which way you're looking at it, each player has 8 pawns, 8 indistinguishable pawns. I mean, that's where they might start off at the beginning of the game, but we're looking at where could they possibly end up, at some far point in the middle of the game. So those 8 pawns could again have appeared in any order and still look like the same configuration. So I won't go into the details of it, but this is the equation or the formula that Shannon came up with for this estimate of the state space size. So you've got that 64 times 63 all the way down on the top, but then you're dividing by 2 6 times because of all those pairs, and then you're dividing by this thing 8 factorial, which if you don't know what 8 factorial is, don't worry about it, but that takes account of the pawns. And there are 2 sets of pawns. That's why it's squared. So this is the calculation Shannon did, and that comes out at about 10 to the power 43, which again is a big number, very big number. And even if you were able to put each individual position and what to do next on one single atom of silicon, your computer that can store all this information is going to have to be quite heavy because 10 to the 43 atoms of silicon weigh 600 trillion tons. So no, that's not going to work either. Okay, but we're still sitting here saying we know there are chess-playing computers. So Shannon says, okay, don't despair, thank you. There are things we can do. What can we do? We can't learn the whole game tree, but we can think a few moves ahead. We can calculate the next few levels of the game tree from where we are. Maybe 3 moves, so 6 plies. So each player has 3 goes. Now that feels like not going to be too awful, too big. Actually, it does get quite big. So even from the beginning of a game of chess, if you do white moves black, white, black, that already, think of what it might be. How many different games have we created by doing that? 119 million. Even with that, it's crazy. Actually, some of those have already finished, right? If Fool's Mate can be done in a very few number of moves. But yeah, 119 million games just in 3 moves. So this is still a lot, but computers can handle these big numbers. So that's one thing you do. Look a few moves ahead and pick the best move based on what, though? Well, you can rank them according to some carefully chosen function. For instance, it's well-known sort of rule of thumb in chess that the queen is, obviously the king is infinitely valuable, but of the other pieces that you can lose, the queen sort of scores 9, I think the rook is 7, and then you work down and the pawn is 1. So you could score the number of pieces that you have left on the board versus your opponent. If you've lost your queen, that's worse than if you've only lost a pawn. So you can rank them in various ways and then somehow pick the best move to play based on looking 3 moves ahead. You can also incorporate some standard openings and end games so that you know what to do in those standard situations. There are still some issues with this. The first one is what's called the horizon problem. Well, that's the main one, actually, the horizon problem. This is where maybe some amazingly brilliant strategic maneuver that gets you to checkmate 4 moves from now, but begins with you sacrificing your queen, if you're only looking 3 moves ahead, you're not going to spot that, so you miss that opportunity. So this problem of the horizon prevents strategies that might be very successful, or things that look good but actually turn out to be catastrophic errors. You don't spot them because they're just over the horizon. Now, this, for early chess programs, this is a huge issue, but developments, including something called quiescence searching, have improved this. So quiescence searching it doesn't uniformly search the same number of moves ahead. It kind of looks at how much of a state of flux the game is if you do that particular move. So suddenly, if you lose your queen, that's a very interesting thing to have suddenly happened. It looks a bit further down that branch than it does for something where nothing much is happening. Maybe you just moved your pawn forward 1 space. So it's not perfect, but these kind of things where there's a way of assessing how exciting or dynamic the game is at that moment and looking a bit further along those branches and less far along others means with the same amount of processing power, you can do a more intelligent search. And with these innovations and others, as I've said, chess programs can now beat even the best players in the world. So chess is complex, it's unsolved, but although it's theoretically unsolved, kind of for practical purposes, it sort of is solved. So are there any harder games? Let's look at what we've got, kind of a few examples so far. We can see there is this kind of correlation between the game tree complexity and whether the thing is solved. So the lowest game tree complexity that we see, your noughts and crosses, connect 4, strongly solved. Strategy from any point. The next ones up, these are quite high, 10 to the 40, 10 to the 50, those are weakly solved. So they can be solved, but not to the same extent. Chess is unsolved with 10 to the 120, but computers can beat us. So if we use, as a proxy for hard, highest game tree complexity, is there a game that's harder than chess? Now, there are some games, but I'm not going to talk about them. I've got sort of 5 minutes. I'm going to talk about a particular game that is played by millions of people. I'm not going to talk about infinite chess or billion by a billion domineering. Yes, those would have higher complexity, but no one's playing them. One game that people do play is Go. This is a very ancient game. You play it on a 19 by 19 grid, but it's not 19 squares, it's 19 lines. And you put your stones, the counters are called stones, on the intersection points there, on the points. The grid points. And this game, it's a strategy game. The aim is to capture territory. So just little examples. Beginners are advised usually to play on a 9 by 9 grid, i.e. essentially like a chessboard. You've probably got one of those already. So what you do is you try and capture territory. Black goes first, then white. You alternate. You put your stones on the grid points, and you try and capture territory. So at the end of the game, anything that is completely encircled by either your colour stones or the edges of the board is yours. You can also take prisoners. So that thing, that letter A there says at some point in the game, this is a finished game that we're just showing you, at some point in the game, there was a white stone there, but then black engulfed it, as you can see happening in the right 2 pictures. And when that happens, when black or white completely encloses a counter of another colour, it takes it prisoner. So at the end of the game, you count up how many points of territory you've got, and add on any prisoners you've got. You get a total. In this example, black has 16. But white, even though white has no prisoners, white has more territory. So white wins by 1 point in this example. Now, there are some subtleties, which I'm not going to talk about, that prevent things like constant flip-flopping between two states where you constantly are taking a prisoner and then being captured and losing a person and then winning a person again. So the Ko rule, for example, deals with that kind of situation to avoid an eternal game. That comes from, I believe, the Japanese word for eternity. So this game then, Go, how complex is it? Oh, by the way, yes, plug for British Go Association. Or see association in your country, wherever you're watching this. But those diagrams come from their website. They kindly allowed me to use them. And there are loads of people across the world who play Go. So if you're interested, there you will find many friends who will play with you. So how complex is Go? Let's do a comparison with chess. State space complexity of Go, so the number of possible configurations. Chess was about 10 to the 43. What about Go? It's got, so the little Go board there, 9 by 9, that means there are 81 places, 9 squared, 81 places that you can put counters. Each one at any point is either empty or has a black stone or a white stone. So 3 choices, 81 points. That's about 10 to the power 38. Not too far off chess. But 19 by 19, which is the standard size, now there are 19 squared places you can place your counters, and 3 to the power 361, which is 19 squared, is about 10 to the power 170. A 1 with 170 zeros after it. Way, way, way hugely more complex state space than chess. What about the game space complexity? Chess, 10 to the 120, that's Shannon's number. In Go, you can do the same kind of estimate. This time, an average Go game lasts 150 plies on average, and the branching number this time is ridiculous. There are, on average, 250 moves you can make. And so when you combine those together, you get a crazy game tree complexity of 10 to the 360. So again, way, way more complex than chess. So where does this leave us in terms of computers? Computers can beat us at chess. What about Go? The techniques that allow computers to play chess quite often are going to fall over with Go. It's just too big. But there are ways to attack it. So can a machine ever beat us at Go? Well, let's see. Nowadays, we have AIs, and so an AI called AlphaGo was one of the first to combine Monte Carlo methods with deep learning. So what does that mean? Well, Monte Carlo methods are, what you do is, each point, instead of going like many, many moves ahead, you try out a move, and the way you test it is you do that move, and then you play against yourself, let's say 1,000 different games, at each point choosing at random what to do next. So you play 1,000 or 10,000 random games to the end and see who wins, and then that gives you a kind of a weighting for that move. The one that wins the most random games in this process is the one you're going to pick. And the learning is because you then remember and you learn by your experience. So AIs like AlphaGo have, through this and other techniques, become very, very good at Go, to the extent that in 2016, AlphaGo beat the then world champion at Go by several games, and, okay, is it all over? Well, it's not quite all over. I have good news for you. This very year, a human bounced back, came back, and beat a top AI by a massive 14 games. And the way he did it was to exploit exactly the horizon problem we mentioned in chess, that these machines are very good, but they can't look too far ahead, even with this Monte Carlo thing. If there's a really good strategy, but it's, that's one thing to do out of a million choices, the computer may not see it. And indeed, he exploited this. He played a really long-term strategy that the machine did not see coming until too late. So there is hope for the humans. There's hope for the humans still. We'll see how that one continues to play out. So we love board games. We love them because in our leisure time, we like to use our brains. That's why you're all here watching this lecture. We don't like to just sit around. We like to use our brains, and playing games is one way of doing it. Solving puzzles is another. And that's going to be the subject of my next lecture, which you're very welcome to come along to, on the maths of Sudoku. But for now, I will stop. Thank you very much.
Okay, so we've got time for a couple of questions. Remember, if you could use the Slido, and the good news is if we don't get time to get to the questions, if you send them to Slido, there might be a chance that we'll be able to come back to Sarah a bit later on with our podcast series, Any Further Questions. So don't worry, we will try, if you've got a burning question, we will definitely try and get it to Sarah one way or another. However, we do have a couple of questions to start off with now, Sarah. So I'm going, where is it? Here we go. So we have one question. Are quantum computers likely to be able to solve chess? And to which I think we could safely add Go there too. Now, I don't know how au fait you are with quantum computing.
So, when I was researching this talk, that exact question occurred to me, and I thought, maybe it's like we hear they're going to, smash cryptography, quantum computers. So I had a little look at this, and it seems that, in fact, not necessarily. In that the things that quantum computers are super good at are not quite what you need to fully search a game tree. So as far as I can tell, actually it's not going to be a magic bullet for this, unless some amazingly wonderful new concept is thought of. But at any point we can invent a new method. So with these new methods like quiescence searching or Monte Carlo search methods, each of these have been overused the word, but game changers in this space are suddenly revolutionizing what's possible. And Go playing computers went from amateur level to Dan level of brilliance super fast when Monte Carlo search was incorporated. Yeah. So who knows?
And maybe sort of connected to that, we've got a great question here about how do people use maths in actually coming up with board games, do you think? And then, we could add on to that. Maybe that's what quantum computing could do. It could generate new ideas for games.
Yeah, so that's a good question. I think if you're designing a game, there are some, even at the most basic level of, if you're rolling dice, we haven't talked about that kind of game, but if you're rolling dice, what do you want the outcome to be? And for that, if you understand what the most likely outcome of a dice roll is going to be, so if you roll 2 dice, the most likely total is 7. So throwing a 7 has to be something that it works in your game to happen a lot, whereas throwing a 6 or an 8 is slightly less likely. So understanding those kinds of things, even at that level of mathematical understanding, that is going to help you with game design. So there's all sorts of ways that mathematics can contribute to designing games that are fun to play, not too hard, not too easy, which really matters.
Hi, my friend and I used to play 3-dimensional noughts and crosses every night. Until we'd got to the stage where whoever started always won. So I'm assuming that is strongly solved.
Yes,
But
I think
how many dimensions would you have to go up to until it's not?
Well, now. How many dimensions have you got space for in your house? So if you have a handy Tesseract, it'd be fun to see the 4-dimensional version. All of these games, you can make bigger. So you can make a game where instead of getting 3 in a row, you have to get 4. Or the board is much bigger. Or, as you say, you can go up higher dimensions. And even, so infinite chess that I mentioned, that isn't a joke. There really is a game of infinite chess. You have an unlimited square board. You set up your chess kind of configuration as normal, but then the pieces can move however they can move. So a pawn can still move 1 forward, but the queen can go as far as she wants in any direction. So that is a game, and that's going to be very, very hard, and certainly is not solvable. Well, I shouldn't say that. It's not solved yet, let's say. Yeah.
So we play a game at home called Prison Rules Scrabble, which is quite similar. It means that anything goes. Very weakly solved, that one, I think. So we have an inquiry here. Why didn't you mention hex?
I know, I knew this, yes. So hex is a very well-known game among mathematicians in the community of combinatorial game theory, I think it's fair to say. So this is a game that it's, I believe, ultra-weakly solved, that there's a known strategy, and you can do it by this strategy stealing method on a big enough board. But I didn't mention it because I wanted to concentrate on games that most people would have played or be at least a little bit familiar with, and hex is less so. There are brilliant resources on hex online, and it's a very fun game, hex, because of the hexagonal array. But just focused on the games that most people will know, I guess.
What is meant by a game being Turing complete?
Right. Well, I think that what it means is that it is hard to... You can't quite prove that these things are impossible to solve because maybe something comes along and we can do it. But it is equivalent to other problems that we know are very difficult to solve, and there's no algorithm that can do it within a reasonable length of time, let's say, without getting too technical. So probably that is what is meant by that.
Okay, and then we do have just one which may be more of a comment, but... someone interested in why the hexagons in the campaign of North Africa, which is quite possibly the most scary game I've ever seen. That's Christmas taken care of. And by the way, have you found In the heart of the sea, Nathaniel Philbrick.
Okay, no to the second question, but I will obviously be looking that up right now. Why they're hexagons? It's actually because, so what are your choices if you want things to fit together seamlessly? You could either have, I mean, this is sort of the mathematics of how shapes fit together, but you could either have squares, or you can have hexagons, or you can have equilateral triangles. So I don't know exactly why hexagons were chosen over squares or triangles, but that is basically, you've got 3 options, really. Yeah.
Brilliant. Okay. Well, please join me in giving a really warm thanks to our speaker today, Sarah Hart.
Thank you.